All right, this is number 4 in our packet. We have a coin C of mass 5 grams, which is 0.005 kilograms, is placed on a disc, the distance 0.14 centimeters. Oh, I see a mistake. We'll assume that that is 14 centimeters or 0.14 meters. From the center, as shown above, the disc rotates at a constant rate. That's pretty important. That means omega is constant. That means the acceleration and the angular acceleration is 0. That means the tangential velocity magnitude is constant. And the acceleration tangentially is 0. But the direction is changing, so there must be centripetal acceleration towards the center. Towards center. That's what's causing the tangential velocity to change direction. Okay. So on the figure below, I'm sorry, the coin does not slip, all right? And the time it takes for the coin to make a complete rev is 1.5 seconds. I just gave you t. The figure below shows the disc and coin as viewed from above. Draw and label the vectors on the figure below to show the instantaneous acceleration. So what's acceleration? And the linear velocity vectors for the coin when it is at the position shown. So when it's at the position shown, the only acceleration is the centripetal acceleration, because the angular acceleration is 0, the tangential acceleration is 0, and the velocity vector is straight up. It is perpendicular to the and centripetal acceleration, and that's what it looks like. Determine the linear speed of the current coin. Well, it's in circular motion. I'm probably going to need this centripetal acceleration relationship, and I'm probably going to have to sum things inward. Well, if I sum the forces inwards, it's equal to the mass of the coin times the velocity of the coin square. Actually, what do we know? We don't know tangential velocity, but we do know something about its period, which is related to its angular velocity. So I'm going to use that relationship. And that is equal to the static friction. If I look at the side view of well, here is the axis of rotation. I have force normal, I have force of gravity, and I have force of static friction inward. Okay, so they want the linear speed of the coin. Well, actually, I didn't even need to sum the forces yet to do that. I could have just noticed that I have a relationship between linear speed and omega. All right, I don't need this yet. I know I'm going to need it eventually. So I know t is known, and that is 1.5 seconds. I know omega is equal to 2 pi over t. So what is omega? Actually, let's just go ahead and plug this omega into Vt. So Vt is equal to R times omega, which is 2 pi over t. And the R was given to me as, what was the radius? I have 0.14 meters. I have 2. I have pi, and I divide by 2 seconds. And that gives me meters per second. And I find that to be 0.586 meters per second. Okay. The rate of rotation is gradually increased. The coefficient of friction between the coin and the disc is 0.5. Determine the linear speed of the coin when it's just about to slip. I am now at max. So now I'm going to sum the forces in. Mass of the coin times the velocity squared over radius, and this will be my max velocity, and I will be at my max force of static friction. So I know that force of static friction max is mu s times force normal, and in this case, force normal is mg of the coin. And so I am solving for V max, and I get V, I'm not sure why I changed colors. I am solving for V max, so I get V max squared equals mu s mg times the radius divided by r. Oh, not divided by r, divided by m. Getting tired. What cancels? My m's cancel. I find that the velocity max is equal to the square root of mu s g times r, and I can plug in the values that I know, and that is 0.5 times 9.8 times, what's the radius? 0.14, right? Yes. All right, and I find V max to be equal to 0.83 meters per second. All right, if the experiment in part C were repeated with the second identical coin glued to the top of the first coin, how would this affect your answer? This is when using your equations without numbers make your life easier. In part C, we found V max to equal to the square root of mu s times g times r. The increase in mass will have no impact on the max speed. Okay, as mass goes up, force normal goes up, force of static friction max goes up. All right, that part probably wasn't necessary. I just happen to know that that's what's actually happening. I think my first part of that question answered it. All right, a ball. We've already worked this, so I'm going to go through this quickly. On the figure, we've done this together in multiple problems. Here's my force tension. Here's my force of gravity. Determine the mass of the ball. How we do that is we got to break that tension force. Actually, I'll keep it black. Tension into its components. We have T sine theta, and this is T cosine theta, and this is mg. And so we can sum the forces in the y direction, which is 0 because acceleration is 0, and it equals tension cosine theta minus mg. And we find mass to be equal to T cosine theta over g. Now, the terms that I'm allowed is theta. Express your answers to the following in terms of the given quantities and fundamental constant. So did we answer it in terms of what was given, L? Yes, we did. So T was allowed. So what did they give us? They gave us T, theta, and they gave us L. Determine the speed of the ball. Sum of the forces N is equal to the mass of the ball. Did they give us the mass? No. All right, v squared. They didn't say angular speed, by the way. So we actually have to find the linear speed. And the force inward is t sine theta. And so if we rearrange that equation for the velocity, we find the velocity is equal to t sine theta, all of that times r, divided by the mass, and we take the square root. Now, we have to get the terms that are not allowed are mass and radius, okay? So we have mass in terms of things that are allowed, but we got to find radius. So what is the radius? Well, we know this is L, this is R, and we have theta. And so sine of theta equals R over L. So R equals L sine theta. So I can plug those in and I get velocity is equal to T sine theta times the radius, which is L sine theta, divided by the mass, which is T cosine theta, and then G will be back up here. So velocity is equal to, T's cancel, one of those sine theta, so again, sine theta over tangent theta, oops, that's not what I meant. I was jumping to it. Sine theta over cosine theta equals tangent theta. So tangent theta L sine theta over G. There's your answer to C. Suppose the string breaks and the ball swings in its circular path. Where? Oh, it's horizontal. So if I'm looking at it, it would become a, the ball becomes a horizontally launched projectile with a parabolic path. Bx initial equals the tangential velocity, Vy initial equals 0. All right, we'll see. We can also be even more descriptive if we wanted to. Acceleration in the y direction is equal to negative g, assuming down is negative. Acceleration in the x direction equals 0. All right, that's my solutions for that particular problem. And I will do the next two in a separate video.